Hello, thank you for joining us. I want to give particular thanks to those of you who are in Asia and Australia that are joining us late on a Friday evening. We really appreciate it. Welcome to this presentation, which is part of an ongoing monthly Goose webinar series exploring issues and projects associated with global sustained ocean observing and the observation of essential ocean variables. My name is Albert Fisher. I'm the director of the Global Ocean Observing System Project Office, which is based at the Intergovernmental Oceanographic Commission of UNESCO in Paris, and I'll be moderating today. During the next hour, we'll start with a 30-minute presentation from Brian King on Argo, Revolution and Evolution. And after the presentation, we'll conduct a question and answer session by chat. I'll moderate and select and ask the questions verbally, and I'll try to select questions that are representative. And we will try to answer as many questions as time permits. The chat window, which you'll see on the lower right-hand corner of your screen, will be open during the presentation if you'd like to start asking some clarifying questions. And please note that this session is being recorded, and a link will be posted on the Goose webpage for those who weren't able to join live. So our presenter this month is Brian King. Brian is an expert in ocean circulation and climate, as well as ocean observations from multiple types of platforms. He's based at the UK National Oceanography Centre in Southampton. And he's been a member of the Argo steering team since 1999, so he has seen its incredible growth over the past decade. So I'm going to turn it over to Brian for the presentation. Thank you.
Thanks, Albert. And welcome to everybody. Looking in the participants list, I see a good number of familiar names and also a good number that are not. So I'm glad that there are people here who perhaps will be learning a bit about Argo. So the first thing I need is for Andrea to start the presentation. And so there's the title slide. Yes, a good morning and a good evening to you as appropriate. Hopefully you can hear me okay, and if the sound goes, then I guess Albert or Andrea will find a way of telling me. So what I'm going to try and do is tell you a little bit about things that Argo has achieved and why I regard that as, and presenting that as a revolution in ocean observing, and also to tell you a bit about how Argo is going to develop in the future as far as we understand it amongst those of us who have the wonderful privilege of helping to steer the program along. So the presentation is put together with contributions from a wide range of the Argo community, both within the UK and internationally. So to begin with, just a couple of aspects of Argo that I thought really are so profoundly different from the way observing was done previously that they really can be described as a revolution. And this is not an exhaustive list, but it's just a beginning. So the first thing I put on the list is that one thing that characterizes Argo is the free and immediate exchange of data from the research community. And now this is kind of taken for granted now, but it really wasn't at the start of the program. At the start of the program, the operational groups and meteorological groups, for example, were accustomed to exchanging upper ocean thermal data or sea surface temperature data or volunteer observing ship data, whatever. But really the in situ observations, mainly made from either moored instruments or lowered instruments tethered to research ships, really belonged to the PI who had the funding for a period of time, often several years, before it was released into the community to be used. And what was realized at the outset from Argo is that even though we were operating in very much research mode to begin with very much the same set of research investigators, unless the data were freely exchanged, the program simply could not achieve its goals. So that was something that we set out very strongly right from the beginning. And to my mind, that was one of the first really big revolutions, was changing the way people think about the data and the ownership of data and the availability of data to use. As I say, that is now really taken for granted, and it's been copied by many programs since. But Argo was one of the first to say, this is the way we have to manage our data. Of course, there was unprecedented global coverage combined with good space and time resolution. Global coverage was achieved with ships, but really with very large spacing between ship tracks, even if you got good resolution along track. There was the Upper Ocean Thermal Program, had reasonably global coverage with good good space and repeats in time, but was very biased to the northern hemisphere and did not have salinity. Which brings me on to the third point there, that Argo was really the first program to produce global subsurface salinity measurements with that good space and time coverage. And it completely just really restarted the clock in salinity measurements in terms of what was available. And then finally, one of the other things that was a revolution was agreement between nations to provide access to EEZ waters. This was something that the Argo program realized, that a very large and important regions of the ocean were inside 200-mile zones. And so agreement was reached at IOC level that so long as there were procedures followed, that floats had to measure specific parameters, the data had to be made available freely in real time, and the deployment of floats had to be notified through the International Coordinating Office. So long as all those things were done, floats could be deployed and could drift into international waters, and data could be made available. And this was another real revolution in the way that data were handled. So just a word about the beginnings of Argo. The idea of mutually buoyant floats, that is to say a float you could deploy from a ship and it would sink to a predetermined depth, was really pioneered in the mid-1950s by Stommel and John Swallow from the UK. And the story that I've always been told is that people thought, I wonder if you could have something that would sink and then operate at a predetermined depth. And everyone knew perfectly well this was simply not possible. Except John Swallow came along from a little bit outside the field. He hadn't heard that it was impossible. So with an unfettered mind, he was able to go away and build one, unfettered by this prior knowledge that it couldn't be done. So I don't know if that's true, but I like it as a story in the beginnings of Argo. The first devices emitted acoustic signals, and you located them by listening for the acoustic signals. These days, of course, they're tracked by satellite. And there should be another slide coming up. So this slide really tells you something about the growth of the array for those who aren't familiar with it, and tells you where we are now. The panel at the top is from 2 days ago, the download. Each of those black dots represents one active float. So there are 3,500 active floats as of 2 days ago. And as you can see, with global coverage and more or less random distribution. Some pockets of floats in particular regions, for example, in the Northwest Pacific, the coastal states there have particular interest in those regions. They've deployed extra floats for research purposes, but there's global coverage achieved by international cooperation. Around 30 countries contribute to that. In the lower right-hand corner, you'll see 30 flags. If you don't see your national flag there, either it's an omission or it means that your nation's not yet contributing to Argo and you need to get onto your funding agencies and get some floats in the water. In the lower left, you see not all the designs of floats, but 5 different designs of floats currently in use in the program, and they're all recognizably similar in the sense that they're cylindrical pressure cases. They all have a bladder for buoyancy at the bottom, and an antenna and a sensor assembly at the top. And then in the middle of the bottom of the panel, you see an indicator of the growth of the array from about 2001, the array was growing quite fast, and the red horizontal dotted line is 3,000, which was our original target for the size of the array, the number of active floats. And you can see that in about 2007 we reached a target of 3,000 active floats, and the numbers have been reasonably stable and gone up and down a bit, but grown a little bit since then to the array's present size. So here, for those who aren't familiar, a schematic of what floats do. You can see in the left there's a little animated GIF there. It basically shows at the bottom of the GIF a bladder. There's a rubber bladder and a reservoir of hydraulic oil inside the hull, and that oil can be pumped out to expand the bladder and give you extra buoyancy so you can come up to the surface. You can suck the oil back in so that you lose buoyancy and you sink. And then in the right-hand panel you can see the schematic showing a float starting on the surface, sinking to some drift depth, usually 1,000 meters, drifting there typically for 10 days, and then finally sucking in the last of the buoyancy, so you sink to the maximum depth of 2,000 meters, whereupon you pump your bladder out fully, rise to the surface, making measurements as you go. So that's where our main profile measurements come from, and then broadcasting the data back by satellite. And a typical float is measuring temperature and salinity, or conductivity, but salinity derived from it. So those are the primary measurements that our floats make. Now this is supposed to be an animation which I'll need Andrea to play for me. We couldn't make it play. So when the animation plays, you'll see this is from the start of the array, the number of floats. And so each dot represents a float appearing. Every now and then you see a ship goes across and deploys floats, so you get a sudden spurt of extra floats. It seems to have just frozen there. I guess it'll pick up in a minute. And by about 2007, which is coming up soon, the array has reached its stable size, which means the floats are dying as their batteries become exhausted as quickly as they're being redeployed. And these wonderful animations, they're on a website maintained by Howard Freeland in Canada, and you can get them for regions of the oceans, for the global ocean, for the Southern Ocean. And if you go and get some of those and look at them, you can see there are little tails that show where the float has been. You can see all kinds of wonderful features in the ocean. You can see the Antarctic circumpolar current, all the floats moving to the right. Towards the bottom of the panel, you can see equatorial jets, you can see the western boundary currents in the Kuroshio, the Gulf Stream, whatever. So that gives you a sense of the coverage. And now we'll revert to the main presentation. Okay. So just to think about what it takes to sustain the program. The lifetime of the floats is round about 4 years at the moment on average. The engineers are working hard to improve that and make the floats last longer. But with a lifetime of around about 4 years, and typically it's the batteries become exhausted that causes the float's mission to end, you need about 800 floats a year to sustain the core array of 3,000 or so active floats. And each float has a lifetime cost of about 25,000 US dollars. So there's the float hardware to be paid for, there are deployment costs, data transmission by satellite, typically 150 profiles to 2,000 meters from each float. There's data management, not just the collecting and serving of data, but the quality control as well. So the overall cost of the core array of about 3,000 floats is something like 20 million US dollars per year, and that is the sum of contributions from the various national programs that contribute. We don't get any central block funding, but each national program secures funding from its national agencies, and that adds up to around about $20 million a year is the cost of maintaining the program. So a little bit about science and what sort of science and research has been done with Argo data. The first thing to point out is that something like 1,500 research papers have so far been published that have used Argo data in one form or another, whether it's analysis of ocean circulation or things about climate change, assimilation of data into models or whatever. So what does a typical float collect? So here's a vertical section, its depth versus time, made from the data from one float. This happens to be a particularly long-lasting float. And what we're seeing here is the colored contours, the coloring is salinity, and the white lines that you can see over the top are temperature. And what you can see is in the early part of the float's life, up until about 2010, just by looking at the periodic appearance and disappearance of the darkest blue, that's the seasonal cycle in salinity observable near the surface. And the float having drifted kept reasonably in one location for much of its life and observed that seasonal cycle. In the last couple of years, 2011-12, you can see it's drifted into a new ocean region where it's encountered much higher salinities. And the floats, we have no control over where they go. They simply drift wherever the ocean currents take them. So if you want to study a region, you have to have some way of combining data from different floats in that region. The primary measurement, I think, that has been exploited to the greatest extent with Argo is, of course, the temperature, which tells us about ocean heat content. Now, this, I'm sure, is familiar to all of us, but I think it's always worth rehearsing. Why is ocean heat content so important? This is because something like 90% of global warming takes place in the ocean. Of course, we all experience global warming through and global change through atmospheric conditions. But in terms of the energy budget and heat coming in and heat going out, all of global warming basically is taking place in the ocean. The air doesn't weigh very much, so it doesn't take much energy to warm it up. The land is solid, so it's very hard for heat to penetrate more than a few meters below the surface. The permafrost remains permafrost. But the oceans can move and mix, so extra heat can penetrate into the deep ocean relatively easily. And that's why, in terms of the global energy balance and physics, global warming nearly all takes place in the ocean. And if you want to know about the global energy budget, it's the oceans where you have to look. So here are some, we'll shoot through some examples of the kind of science that has been done with float data. This is some data from 2014. You may not be able to see the panels, but these are vertical slices of temperature anomaly along the equator. So it's down to about 300 meters and across the width of the equator. And you can see in the left-hand 4 panels from top to bottom, early January, mid-January, early February, mid-February, these are temperature anomalies in 2014. And what you can see is a progressive warming growing from west to east, and cool anomalies disappearing off to the east. And by you get to the right-hand panel, you now have a significant amount of the Pacific is warm below the surface. And this means that forecast centers are now predicting El Nino conditions for later this year in 2014. So a lot of this has traditionally been measured with moorings, but as the data return from the moored array has dropped off a bit in recent years, Argo has taken up some of that slack in providing some of those critical temperature data, for example, to enable and support El Nino forecasts. The next sort of area, this is a picture from some colleagues in Australia, and it shows how our ability to simply describe the ocean in a climatology has improved in recent years. Using data up to the year 2000, you get the bottom panel. This is the ocean south of and surrounding Australia. And early in the series, the ocean is very smooth because you have to accumulate an awful lot of data, an awful lot of years of data to get anything like a map. As Argo begins to come into play in 2006 and finally 2010, as you move up to the most recent, you can see that the ocean can now be described. If you want to say, what is the ocean like now and how will we tell if it has changed in the future, it can be described in much greater detail because Argo data have come along. So the question is, why are we able to do so much better a job now? Let's just make that advance. So why do we so much better a job with Argo? Here's a picture made by Howard Freeland in Canada. Again, and the lower panel here, I'm going to show you another panel in a minute. This shows the distribution of all historical observations. So if you look in the historical database prior to Argo, all historical observations, and you divide the ocean up into 1 degree squares, and then you color the square by how many observations you had, white squares had no observations. So the white squares, all the white areas in that lower panel means that ships have never been there. There has never been a profile of the ocean done from a ship where the square is white. It's never happened in the entire history of ocean observing. The blue ones, or the black ones, are 1, and the blues are 2 to 5. So the majority of these ocean squares have had fewer than 5 observations in the entire history of ocean observing. And that is the information that we have to make estimates of climate change and so on. If we now see what Argo has done, whereas the entire history of observing had 500,000 profiles, my webcam seems to have gone off, I'll restart it. The entire history of ocean observing had 500,000 profiles. Argo managed 1 million profiles in the first 10 years of the program. And you can see now there are no white regions. They're mostly yellow regions or pink. And yellow means at least 6 and pink means at least 20 measurements in each 1 degree square. So that is the way that Argo has now completely dominating the supply of new data to understand things like global heat content, freshwater cycling, and so on. Of course, ocean change is not uniform everywhere. It's not the case that everything is just getting a little bit warmer. This is a section, again, it's a vertical slice from south to north and averaged east-west, showing regions of the ocean that are getting warmer and regions that are getting cooler. So the yellows and reds, the ocean is warming. The blues and greens, the ocean's actually cooling. So it's not uniform warming everywhere. But it does emphasize to us the fact that if you really want to understand the heat budget, you have to look everywhere and add up with complete and comprehensive sampling what's going on. You can't just sample some regions of the ocean and leave others unsampled, or you may lead to wrong conclusions that way. So there's a picture of ocean warming and the geographical distribution of it. So our ability in the future to be able to say whether change has taken place will be much more robust because we have much better and more comprehensive climatologies now. So in many ways, the clock has been reset for comprehensive and reliable estimates of ocean heat content. The next thing to look at, a couple of pictures here to address this question of the so-called hiatus in the increase of surface air temperature. So the left-hand panel here shows surface air temperatures, and the right-hand panel shows ocean heat content. And the particular regions of interest are the ones that have just come up as circled. So when you look at the air temperature trend, what was observed is that since about 2000, global air temperatures, as far as they can estimate them, have not really gone up. So the suggestion was, does that mean global warming has halted? But I said, really, all the global warming energy is in the ocean, and the ocean heat content has gone on rising perfectly well since 2000. So in terms of the global energy budget, the Earth is taking up heat at just as good a rate as ever it was. And what I draw your attention to is the estimates of global ocean heat content starting from 1960 at the left-hand end of this panel up to the present. You can see the uncertainty gets dramatically smaller after the year 2000 when Argo data start arriving. And this means that in the future we will be able to detect changes and we'll be able to understand them on much shorter timescales. Rather than having to take a few decades and say, yes, it really looks like the trend is upwards, we will have much more reliable estimates of global trends. And what this also tells us is that surface air temperatures are not a good proxy for global heat increase, for global warming. It's certainly true that you do get some particularly big events, volcano events, Pinatubo, for example, where air temperatures and ocean temperatures go down, but generally they are not all that tightly coupled. One more thing to think about is sea level. And one of the reasons we're interested in heat content is because if you warm the ocean up, then it expands, and sea level is alive and well throughout the period since 2000. Sea level is continuing to expand. And in this left-hand panel here, you can see either from tide gauges or satellite altimeters, you get the black line showing that sea level is rising and is continuing to rise. And the various components of that sea level rise, as near as we can estimate them, the two most important there are thermal expansion of the water that's already there, and of course some added mass from water being added. And with now good estimates of the thermal expansion rate, we can more or less close the budget of sea level rise so that we know that not only do we get the total sea level rise correct, but we know what components are contributing, whether it's added mass or thermal expansion. One more thing to think about is ocean salinity. Why are we interested in ocean salinity? Well, of course, the oceans contain nearly all the free water on the planet, and most of the exchanges of evaporation and precipitation also happen over the oceans. So the amount of precipitation available on land, and therefore the amount of fresh water, one of the world's most valuable resources available on land, depends critically on the water cycle out at sea. And that is to actually measure either evaporation or precipitation out over the open ocean is very difficult, but fortunately the ocean is a great integrator. And so patterns of ocean salinity, and particularly surface salinity, reflect what's going on in the water cycle. Over on the right-hand side, we have the mean distribution of ocean salinity. The highest values here are in the Atlantic, the subtropical North and South Atlantic. Over on the left, we have the estimates of evaporation and precipitation. And basically, the regions where you have the greatest evaporation are the regions where you have the greatest salinity. If you then try and look at trends over 50 years or so, you have to go quite a long way back and look at trends over a very long time because the early data are so noisy. it appears here on the right is the present distribution of salinity. Here on the left, as far as can be estimated, are the trends in salinity. So not only is the tropical North and South Atlantic the saltiest places, it's also the places that are getting saltier. And what we see is that the salty places are getting saltier and the fresh places are getting fresher, which suggests from this global integral that the hydrological cycle is speeding up. And our ability to monitor ocean salinity and make sustained measurements of ocean salinity using floats will enable us to address critical questions about the water cycle and the future of the water cycle. I don't know. The webcam keeps going off, so you can't see me. Maybe you can see me again. I was going to make a couple of remarks about combining Argo data with some other measurements, but I'll skip over those and move on to something about deep measurements. So here's a picture that's become very familiar in recent years. A paper published by Sarah Perky and Greg Johnson in 2010, and it shows from ship-based measurements, it shows that much of the deep ocean is getting warmer. A particular interest to us, and this is the basically warming or cooling of the deep ocean deeper than 4,000 meters. A particular interest to us in the UK was this northeast Atlantic basin, which they suggested was getting cooler. The only basin where the cooling signal was greater than the uncertainty. Plenty of places where the warming is greater than uncertainty, but the northeast Atlantic was the only place where cooling was greater than the uncertainty. So we've been doing some work here in Southampton where we've taken 3 lines, the lines shown in black in this panel, which have been occupied by ships quite often since the 1990s, a total of 13 or 14 cruises along those tracks since 1990, some in the 90s, some in the Argo era of the 2000s, and we made an estimate of the deep ocean temperature change from those cruises. And this is summarized here. In the upper ocean, we've looked at Argo data. We've analyzed the Argo data and analyzed warming in Argo data, and that's the red line with some uncertainty. And this is the trend, the warming trend, and here's the 0 line is down the middle of the panel. So much of the upper ocean is warming. In the deep ocean, we've only had shipboard data to look at. And while since 2000, we've concluded that there was no significant cooling since 2000. The right-hand panel shows that if you divide those ship-based data into data before 2000 and data after 2000, you actually get 2 different estimates. So the 90s looks like it was cooling, which is pretty much what Perky and Johnson said. Since 2000, we think it's been rather stable. But this is one of the best observed basins, the Northeast Atlantic, with a lot of lines that have been occupied by ships quite often. And even there, it's quite hard to tell exactly what's going on and to know whether a signal that you get from looking at ship measurements 5 or 10 years apart, trying to interpret that signal in terms of trends. So what we need to do is get down into the deep ocean in the same sort of way that Argo's been observing the upper ocean. Which brings me on to the extensions to Argo. Just some summary of what we've seen so far. Observing and understanding the ocean interior is critical for understanding global climate change. The warming, sea level, the water cycle. There is an unprecedented observing capability in Argo, which means we can detect changes sooner and with greater confidence than was ever possible before. Argo has become the dominant source of data for describing the upper ocean, and if we don't sustain the core array, we'll once again become blind. And the extension of Argo into the deep ocean will further increase our ability to understand, predict, and prepare for future changes. So that's the sort of the revolution side, things that can be done in the upper ocean now that simply could not be conceived of or recognized 20 years ago. We now observe the upper ocean in a way that would not have been recognized from 20 years ago. Argo is evolving in a number of different ways, with greater geographical extent, with deep sampling at least to 4,000 and sometimes to 6,000 meters, and with new sensors, mainly bio-optical. So a couple of slides on each of those topics, and then we'll be done. This is the picture that we're looking at now amongst the Argo planning and implementation groups, showing some of those enhancements. Most of the ocean will be covered by the core Argo program. That's what you see in blue. We're looking at enhancements in marginal seas that at the start of Argo we didn't feel able to tackle. We didn't have the resources, we didn't have the technology to be able to tackle the marginal seas, so originally they weren't in the program. At high latitudes, we want to start going under the seasonal sea ice, which originally we excluded. We said the ice-free ocean. Now at least we can go under the seasonal ice-covered oceans, but not if you want to go under permanent ice. You need different technology. The western boundary currents, we realised that, or what was already known, that in regions of the western boundaries, you need to resolve at smaller horizontal scales than Argo presently does. And so we're now looking for enhancements to increase the density in the boundary regions. And I said in the tropical Pacific, Argo's trying to enhance its sampling to take up some of the slack left by the not incomplete data return from the tropical Pacific moored array. So new missions. Here is the same picture of deep ocean heat changes. Here on the left is what is likely to be achieved in the next 5 to 10 years by ship-based measurements. This is the GoShip program. That is the network of lines that it believes it can occupy from ships. Ships have the huge advantage that they get you right into the deep ocean, and they measure the parameters, all the biogeochemical parameters that Argo can't measure. So Argo is not going to replace ship measurements in the deep ocean, but in terms of things like deep ocean heat content, it can supplement the ship program with the kind of resolution that you've already seen. So there are lots of requirements there in terms of understanding the sea level budget and the heat budget. In terms of readiness, deep floats are being trialled. This month, there will be a trial of a couple of deep floats in the Southwest Pacific, and particularly of the sensors. New sensors of ultra stability are under development for deep measurements. Where we're hoping to go next with this is with a regional pilot to refine deployment plans, to prove the technology, try and improve the cost effectiveness, and, as I said, to help design a global array. A deep float will not look like a cylindrical pressure case. The pressures are simply too great for that approach. So many of the deep float, the real 6,000 meter deep float designs are going to basically have spherical buoyancy rather than cylindrical buoyancy. You can get to about 4,000 meters with cylindrical buoyancy, as here on the left, but in order to get to full ocean depth, the float will have spherical buoyancy, so they won't be instantly recognizable. Other new missions we're looking at, the addition of biooptical sensors. The reason these are needed are to improve regional biogeochemical budgets, so that people who want to do research on those topics can get access to the same kind of density of data of both space and time resolution that physics analyses presently enjoy. There is a move into biogeochemical numerical modeling, and those will need data sets to initialize and verify them. How ready are we? Already about 200 floats carry oxygen, but understanding how to distribute those data and do the quality control is still a work in progress. Other sensors that are being trialed include nitrate, pH, fluorescence chlorophyll, and others. Lots of challenges there in terms of sensor stability, understanding how to do the data quality control, understanding what the data management protocol should be, even understanding how to distribute those data, because the volumes of those biooptical data are an order of magnitude larger than the volumes of physical data. And then finally, the EEZ sensitivity becomes quite high for some of these biooptical parameters, which under certain circumstances can have implications for resources and so on. So initially those experiments are all going to be out in the open ocean. Other new missions we're likely to see, there's an interest in near surface profiles. Many traditional Argo floats stop measuring at 2 meters or 5 meters, and some people would like measurements right up to and through the surface. So either with dual sensors or certain kinds of sampling, we hope to get closer and closer to the surface. There are other missions, for example, frequent shallow profiles for near-term forecasting, for example, of hurricanes. People would like to put profiling floats into hurricanes to get real-time data. And people would like to move on to the shells, which are presently undersampled. So you need a different kind of sampling strategy and probably different hardware altogether. So all of those missions are possible, but are likely to have lower accuracy data. And each mission really will have a different data quality target, and the data system will need appropriate resources to deliver the different requirements of the new missions. So just by way of finish, I think progress in oceanography follows largely from the development of accurate and cost-effective new technologies. Often when you get a fundamental new technology, you get fundamentally different kinds of research being done and breakthroughs in terms of concept, of understanding of the ocean. In the last 10 years, Argo has really revolutionized our ability to collect temperature and salinity data from the oceans. It's the only technology able to provide that kind of global space and time coverage. Over the next 10 years, it's likely to have a similar revolution in terms of biogeochemical data. I think we'll see physical measurements will evolve, biogeochemical measurements will be revolutionized. Argo, of course, remains a key data set for global change studies. We're now producing something like 120,000 profiles every year. And I think in the coming decade particularly, we'll see Argo extended into the deep ocean, the marginal and coastal seas, seasonal ice zones, and including new biogeochemical sensors. And then there are just a couple of links there at the bottom. w.argo.net is our main information portal. Argo.ucsd.edu is the project webpage hosted at the Scripps Institution. So I think that's it. I'll finish just by putting up a picture that summarizes some of the different participants, and thank you all for your attention.
Brian, thank you very much for that talk. It was very informative, really a great history of the evolution of the Argo float array, and some good material about your future plans. So we've enlarged the chat window. Thank you for the applause, all for Brian. And I'll encourage you to ask questions. Katie's already asked a question. I have a few that I've stored up. So please go ahead and ask your questions, and I will select questions that I think hopefully ones that are representative for the audience, and ask them to you, Brian, for responses. Okay. So let me go back to really, I'm curious about the challenges for sustainability of the Argo array. We have seen a great evolution, great growth, a real change in the climate science, particularly you talked about, that was enabled by this array. So what are the challenges to sustainability? Are there some general statements you can make, or does that vary very greatly from country to country?
No, I think there are certainly some general statements. One of the challenges which should not be overlooked is the technological one. It's easy to imagine that just because we know how to do this now, that all we have to do is carry on doing the same thing. And I think what we've seen in other programs, and we sort of take lessons from other programs, is that if you just say, this is now routine, and you technologically take your eye off the ball, then you start making mistakes and the performance of your array goes down. There are continual changes and slight modifications to the technology. We've been caught out by a few ourselves, but it's very important that engineers really remain vigilant to ensure that the quality of performance of the floats is maintained. The second thing is a resource question, of course, maintaining resources. We know that we're in a world where funding is tending to remain level. The costs are going up, so everything has to become more efficient. And in particular, the thing that we're aiming to do is ensure that our floats last longer. So the engineers are working hard to increase float lifetimes from 4 years to 5 years to 6 years and beyond, which means that we can do the same job with fewer new floats every year. So there's the resource question of simply maintaining a funding stream to keep deploying floats. And the technological challenge of making sure those floats keep performing, because if you just stop watching it and say this is now a done deal, the quality of the array will go down, and that other programs have seen that and suffered from it by taking their eye off the ball.
One of the extensions that you've talked about, and in fact, so there was a lot of interest even 5 years ago at the OceanObs 09 conference to add new sensors to Argo. Yes. So that, part of the technological challenge as well is that's part of an evolution of the system. What are some of the things that you're watching out for there, and how do scientists get involved with new sensors and Argo?
Well, again, partly it always comes down to resources, and I hesitate to harp on about resources. So, what the view that the central leadership of Argo takes is that if people come along with ideas for new sensors and new research that can be done with it, then they need to bring the resources with them to do that. So, absolutely, Argo welcomes new scientific initiatives. So long as they do not interfere with the core program. So where somebody says, I can get 10 or 20 of this sensor to make that measurement, can I put it on the floats and use the floats that Argo is already deploying? Then the answer is often yes. But if it means that those floats consume their batteries quicker, then we will expect that to be compensated to ensure that the core array doesn't suffer. In terms of science, the biogeochemical community is very active. It has scientists and engineers actively participating in annual meetings to discuss progress, to discuss which sensors are ready for deployment in a pilot basis, which are ready to be deployed in rather larger numbers, and that there are both the scientific discussions and the technological discussions and the data handling discussions all within the rolling cycle of annual Argo meetings. And if any scientist wants to get involved in that, then they can, through the Argo web pages, they will find out what that community of biogeochemical people is, and they will be very welcome to join it and bring along their scientific ideas, their sensor ideas, and to participate.
Thanks, Brian. While we're on the, we're talking about some of the technological challenges and innovations related to Argo, let me ask Eric Lindstrom's question. Are there any innovations in manufacturing floats that will bring down costs and make the system more efficient?
I think disappointingly, we haven't seen the price of a float go down significantly, and perhaps there's just some fundamental baseline about assembling the components. I think the thing that has brought down the overall costs or increased the efficiency is the extension of float lifetimes. At the start of the program, we were seeing floats last perhaps an average of 3 years. Now we're seeing at least 4 years, and some floats going on for 5, 6, 7 years. So its efficiency in terms of data telemetry and reliability in terms of hardware means that it costs you the same to buy a float, but you get a lot more profiles out of it for the same money. So that's the chief efficiency or bringing down of costs, is the not needing to deploy so many floats every year. But the actual cost of a float has remained stubbornly high.
How much of the cost of the Argo array is in human resources and in human activity, such as the data management system and quality control, and how much of it is in the actual technical hardware?
So I think one of the slides I showed suggested that the lifetime cost of a float was about $25K, of which the purchase price of the hardware was about $17K. So that means it's about 2/3 on the hardware. The remaining cost, some of that's telemetry, but other costs are deployment and data management and so on. So you just say probably 2/3 up front to buy the float and about 1/3 to look after the float for the rest of its mission. So that includes producing finished quality controlled data, but not doing any analysis of it.
Right. That actually seems quite an efficient ratio already. Let me just continue again with a few more technical questions, and then we'll go to some other types of questions. There's 2 questions from Etienne Charpentier about precipitation measurements and estimates from underwater hydrophones, whether these are being piloted or deployed. And of the floats that are doing SST profile measurements coming very close to the surface, are those data distributed in real time?
Okay, so the question of hydrophone measurements, this is something that I know that the scientist who I know has done most of this is Steve Reiser, who I saw earlier was online. I don't know if he's still there, and he might like to contribute something in the chat window. Certainly, his group had floats that were attempting to make precipitation measurements, and they wrote some of it up. They had some campaigns in the Bay of Bengal, where they were using hydrophones. So the principle is that by listening to the sea surface, you can estimate how much precipitation is falling. So Steve might like to come in and type something about that. It's not a technology that has been applied widely. I'm not sure whether that's because the components are expensive or because the expertise to interpret the data requires a very high degree of expertise. I think it's not something that most investigators would feel comfortable with. But I would refer anyone who's interested in hydrophone measurements of precipitation to contact Steve Reiser. And then what was the second question that you asked?
There was a question about the profile, the Argo floats that are measuring temperature profiles very close to the surface and basically up to the surface. Are those data distributed in real time?
Okay, are those data distributed? I think I'm not sure that many of those data are being distributed in real time at the moment. The UK has quite a large number of floats that make near surface measurements of temperature. One of the questions until very recently has been, how do you tell the circumstances under which those data are good or not? Because we don't want to be in the business of distributing poor quality data. So certainly early floats that carried that measurement, the data were being thought of very much in research mode, while analysts tried to understand whether the data were good and what confidence could be offered with those data. Whether they've now started distributing them or whether they still regard them as in research mode while they understand what the measurement is, I'm not sure. I would have to defer to colleagues in the data centers about that. If anyone's really concerned with knowing how much of that is circulated, I would refer him to Justin Buck in the British Oceanographic Data Centre, which is one of Argo's contributing data centres. Justin has led some of the discussion about whether those data are of sufficient quality to be distributed in real time or whether they are actually still have too many question marks over them.
So let me ask a question that comes from Christoph Mays. How will Argo, or how does Argo, improve current estimates at the surface and at intermediate depths? You've talked largely about the temperature and the salinity profiles and their impact in climate science, but what have people learned from looking at currents derived from Argo?
Okay, currents. So that was something I didn't talk about at all. Limited time, and I decided I couldn't try and mention everything. One of the things that was initially thought of as being a great delivery from the Argo would be the displacement. And indeed, before floats learnt to make vertical profiles of temperature and salinity, what they actually, the early floats actually measured the displacement. So they only measured currents. Chiefly the current at the drift depth. So you measure the displacement of the float and you assume that's what the current was. In the first couple of years, what we discovered was that Argo displacement data are very noisy, and individual displacements, all that really told you was what happened to that float. It was actually very hard to learn anything about the ocean collectively because you were sampling a lot of mesoscale noise. What has happened in recent years is people have begun to return to that question of ocean circulation, and Michel Olitro at Ifremer and collaborators there have done a lot of work on really cleaning up the displacement data set. So they produced an atlas, essentially a collection of displacements, cleaned up, bad data identified, and so on. So they've got a very clean set of float displacements. And they have then started working on that and analyzing it to produce maps. But what you really have to do, what they found they have to do, is there is so much mesoscale variability that you need to collapse the whole Argo data set into a single mean circulation in order to get something where the signal is significantly greater than the noise. So they've recently produced an analysis that is essentially the ocean circulation at 1,000 meters depth as average from more or less the entire Argo data set. You can't produce sort of monthly ocean circulation maps because there just aren't enough floats and there aren't enough displacements, and the signal to noise is not good enough for you to be able to do that. But a new picture of ocean circulation from float trajectories is emerging.
Thanks. So, you're a climate scientist, and almost all the results that you showed in terms of how Argo had revolutionized our understanding of the ocean are related to climate. But what is the role of climate science versus what some might call operational oceanography or ocean forecasting as a driver for Argo?
I think Argo um, realizes that it serves both communities to the best of its ability. Yes, I suppose I perhaps picked up on some of the global change type things because that's where I'm most familiar, and that's where there have been some very obvious successes. But I think the operational groups, for one thing, Argo makes sure that all its data are available as quickly as we can manage, and that basically means nearly all of it within 24 hours, and there's very little that's not available within 48 hours. And what we notice is that if we have a glitch in our system and those data stop flowing within 24 hours, we hear about it very, very quickly from the operational centers, who get the data either from the global telecommunications system or from our global data centers, where again the data is available complete with quality control flags within 24 hours on the whole. So those groups assimilate data. As I said, Argo has now become by far the overwhelming and dominant source of data for assimilation into any kind of model that assimilates ocean data. We swamp every other source of subsurface data. The operational people very early on told us they want temperature and salinity, that temperature alone was okay, but temperature and salinity was much better than just temperature. So very early on, the operational community was helping to shape the evolution of Argo and the emphasis that we put onto the real-time and quick delivery part of our data system. Every year at our data meeting, we spend quite a lot of time reviewing our effectiveness at delivering those data in quick turnaround, in the quality that our operational users require. And I think the recent discussion about what a tropical Pacific observing system needs to look like. There was a big meeting earlier this year about the tropical Pacific observing system. The realization that so long as we deliver the data in real time in the right way, that floats could contribute a lot to that tropical Pacific observing system and pick up some of the slack that's emerged there. You saw the tropical Pacific enhancement in the global picture that I showed, because it's recognized that floats have a major role to play in that area of forecasting of equatorial phenomena.
So that actually segues quite nicely into a question that's been posed by Katie Hill, which is how have planned Argo enhancements been considered in the context of the capabilities of other components of the observing system? What is the ideal mix of satellite and in situ measurements, including Argo, but including other observing platforms? How is that negotiated? How has it been looked at in the tropical Pacific or in western boundary currents? Is that something that the Argo steering team plans to engage in over the coming years?
So certainly the tropical Pacific, as I said, the tropical Pacific has got its own planning momentum, and Argo was a central part of that, and was the Argo steering team was very much involved in being represented in the tropical Pacific planning. In terms of things like the emergence into deep measurements, for example, and that extension and evolution of the program, Argo is engaged in discussion at the moment with the global ship operators, the GoShip program of sustained hydrographic measurements from ships. Argo is engaged very much with that group in terms of deciding what a deep ocean observing program needs to look like. So there are Argo scientists involved in helping define that, and we actually have at the last meeting of the Argo steering team, and since then in consultation with GoShip, there are plans to have a joint science workshop, very much so that the ship-based observing group and the float-based observing group can come together to both talk about scientific results, but also talk about future opportunities and synergies between those elements of the program. I think in terms of the satellite program, one of the things that everyone wants to know about, of course, is sea surface height and sea level rise, and there is a lot of interface between between people using float data to estimate thermal expansion and that part of the sea level question. Satellites tell you also, of course, about sea surface temperature. And I think there is a debate about whether sea surface temperature or upper ocean heat content is actually the best indicator of the ocean's potential to influence the atmosphere. And I think that's still a somewhat open question, getting a lot of debate.
So in that context, I can actually advertise two past webinars. One was on a deep ocean observing strategy, in which Argo scientists are involved as well. And also an effort to kick off a Tropical Pacific Observing System project focused on 2020. These were the last two webinars, and you can see them and listen to them on the Goose website. So Argo is involved through different Goose projects in looking at what the right balance of observations is. Related to that, what are some of the measurements that Argo, that are not Argo measurements, but that the Argo system depends on to produce really complete data sets for both science and services? What are some of the most closely linked complementary observations of the ocean?
Okay, so yeah, that's a good question. I should have said something about that in the talk anyway. Argo, because one of Argo's challenges is that once we deploy a float, we never get it back to calibrate the sensor at the end of the mission. So we have to think about the data quality and how can we be sure that the data quality is appropriate. And the way that that's done is by comparing data from floats with data from nearby ship-based measurements. So we assume that ship-based measurements, particularly those collected by the Go Ship program and assembled at their data office, which is the Clivar and Carbon Hydrographic Data Office, the CCHDO, hosted at Scripps, assembling really accurate ship-based measurements that are traceable to standards like seawater standards, temperature standards, having those as reference. When a float passes nearby where a ship had been and made a measurement, we can check on the quality of the float data. So for physical parameters, we depend very much on the physical data gathered through the Go Ship program. We can't just anchor Argo data to historical data because we know the ocean's changing. We know the ocean as observed by Argo in the last 10 years is warmer than the historical databases. So it's no use anchoring Argo data to historical data. The ongoing supply of ship-based data that are traceable to standards is absolutely critical. And this challenge will arise particularly when we move into biodata, that we will need the biogeochemical data from ships in order to provide a reference to ensure the data quality of the new biogeochemical floats.
So you mentioned that you never get floats back, which is why you need some complementary observations, and that raises another question, which is more politically sensitive. It's raised by Thanga Prakesh. Does a huge amount of dead Argo floats pollute the ocean since they contain hazardous lithium and alkaline batteries?
Well, so that's a question that we have searched our souls over often and had a number of studies into. I think a typical float weighs around about 30 kilograms, which means that if you are deploying 1,000 a year, it's about 30 tons of floats a year. So that's quite a significant amount. But if you compare it to the amount of, for example, shipping cargo lost every year, it's about one freight container a year, perhaps 30 tons a year of material ending up in the ocean. And when you consider that the shipping industry loses thousands of freight containers over the side, washed off container ships, we're actually relatively small. Then when you think of what a float consists of, most of the float is the aluminium hull. So most of the weight of that 30 tons is aluminium, which is abundant in the oceans already, will eventually dissolve. But that doesn't detract from the fact that, yes, there is a certain amount of batteries and circuit boards and a very small amount of plastics do end up. We then think of the environmental issue of, suppose you went to collect your floats, suppose you ensured that when the batteries ran low, they came to the surface, you went to pick them up. The environmental cost of taking a ship back one by one to pick up floats would be enormous. The amount of extra environmental damage you would do by going to pick up floats one by one would be absolutely enormous. So we believe that the best environmental solution, if you say you want to make these measurements, the best environmental solution is to allow them to die and sink to the seabed.
Thanks, Brian. That's a very good answer to quite a sensitive question. You've clearly given that quite some thought in the steering team. The talk of this, I'm going to end with a very open question, I think, is the talk of this, the title of this talk was Revolution and Evolution. So I'm going to open it up from Argo and actually ask you what you think some other ocean observing revolutions that are on the horizon that could be outside of the field of climate. What are you most excited by in terms of emerging technology and ocean observations?
Well, there are always many, and everyone's got their own pet theories. I think one of the things that is coming along, which is absolutely complementary to Argo, is that of unmanned or is controllable autonomous unmanned vehicles. So essentially gliders and related technologies. I think gliders are continually expanding their range and depth capability. And the big advantage of a glider, although it operates in a rather similar way to the float, is you've got just enough control over it to be able to make particular measurements in particular target areas, which Argo can't do. We only can go where the currents take us. You can be a little bit clever by deploying things upstream and getting washed into the area you're interested in. But there are some things that Argo simply can't measure. And the emergence of gliders is, I think, a very exciting technology and hugely complementary. So I'll pick that as my one.
Thank you very much, Brian. Really, thank you very much for your talk. It was very informative. Argo is really a great contribution to the Global Ocean Observing System and is doing great work piloted by its steering team and supported by all the national Argo programs around the world. So thank you very much, and I will just end with an advertisement for the next webinar, which is coming up on the 17th of June, also at 1300 GMT, so at the same time of day as this one. And that will be given by Tosta Tanua and Maciek Telszewski, who are with the International Ocean Carbon Coordination Project. And they'll be talking about moving towards essential ocean variables for biogeochemistry. So I hope you can all join that event just 1 month from now. Thank you again, Brian.
Thank you all for your time and attention. And good night to those of you who are going to go and tumble into bed.